start, and no doubt Don has a very long road to hoe in connecting the pieces of a very fascinating title. It's a very great pleasure for me to introduce my brilliant colleague, Donald Hoffman. Don received his BA from UCLA and his PhD from MIT in computational psychology. We were very fortunate to recruit him in 1983, and even more fortunate that he stayed with us and added his brilliance to the department. Don's talent was recognized early on by an award from the APA, the American Psychological Association, for early career excellence. He received the very prestigious Trollman Award from the National Academy, and his outstanding teaching has been recognized in the form of the Chancellor's Award for Excellence in Undergraduate Education. Don is an active contributor to research in vision, his main empirical and theoretical focus within the field, but more generally in cognitive psychology, and still more generally in the philosophy of science. His expertise across these various areas will be brought together today in his talk on quantum cognitive sciences. And my reaction when I first saw that title was, "You've got to be kidding me." And then I reminded myself of a quote from Albert Einstein: "If at first an idea is not absurd, then there is no hope for it."
Thank you very much, Jeff. Jeff is in a position to evaluate. He has his PhD both in some work in quantum theory and in cognitive science, experimental psychology. So I expect some good stuff from Jeff.
You see a yellow card.
So it's my pleasure to be here at the INBS, and I'm going to talk about quantum cognitive science. A fundamental assumption that drives research in cognitive science is that mental states and processes are computational states and processes. And in fact, we spend most of our time in practice building computational models of mental states and processes. That's what we do all the time. The notion of computation we use was invented not that long ago. Work by Turing, and Neumann and others led to the notion of Turing machine, and then eventually parallel architectures and neural networks. And so this has been the intellectual framework that has guided most of our model. And one result that has buttressed us in doing this is the strong Church-Turing thesis, which states that a probabilistic Turing machine can efficiently simulate any realistic model of computation, where efficiently means with only polynomial resources in terms of the complexity of the problem. And by realistic, we mean a model of computation which you don't have any hidden resources being deployed. All the resources are being exposed. So, and this was widely believed to be true for decades in the field, and buttressed us in our beliefs that classical computation would be an adequate model for things of interest. It turns out this is false. It's just plain false that a probabilistic Turing machine can efficiently simulate any realistic model of computation. Instead, what appears to be true is that the quantum strong Church-Turing thesis, that a quantum Turing machine, and we're going to explore today what a quantum computer is, can efficiently simulate any realistic model of computation. So I want to explain at the outset what I'm going to be trying to do here today. I'm not going to try to prove that human cognition and brain processes have been shown to use quantum processes in essential. I'm not going to try to prove that today. I'm going to try to instead to change the burden of proof and say, look, we now know that the universe has some computational resources that have been recently discovered. And these new computational resources are superposition and entanglement. And we'll talk about these in just a moment. But there are these computational resources. We know that they exist. We know that they are powerful. And the question is, what evidence, both empirical and theoretical, do we as cognitive scientists have in a particular, in exploring a particular cognitive capacity, that these are not being used? If we want to put out a model that doesn't use these, the burden of proof is now on us to explain why we have the right to ignore or to omit these resources. So it's a burden of proof issue. We now know that these things exist, they're powerful, they can do remarkable things, we'll talk about it. The question is, in any particular case, when we look at a cognitive model, learning, memory, vision, language processing, and we put forth a classical model that doesn't use these resources, the question is, what is your evidence for not having used these resources? Do you have good reasons for not using the resources? So that's the point of view that I'm going to adopt here today. So this is restating that any computational model in cognitive science that fails to exploit superposition or entanglement must give empirical evidence or theoretical reasons for the omission. So now I'm going to talk a little bit about quantum computation. I've programmed in many languages for decades, and I must say that learning to think in terms of quantum programming is a complete stripping of the gears. It's a very, very different way of thinking. So I'm going to just describe a little bit of the new techniques and thoughts. So classical bit can be either 0 or 1. We all know this. Probabilistic classical bit, you can have 0 or 1 with classical probabilities, standard probabilities of p1 or p0. But when you go to quantum, it's a very, very different thing. A quantum bit, the 0 and the 1 can be thought of as the North Pole and the South Pole of a unit sphere. And the state of the quantum bit can be any point on the surface of that unit sphere. The way they usually describe this in quantum computation is they put this little bracket around the 0. It's called a ket 0, so it's a vector. And ket 1 is a vector, and they call this the block sphere of possible states of the quantum bit. And so here is a particular quantum state psi, and it can be parameterized by an angle 2 theta between the z-axis and psi, and an angle phi with the x-axis and the projection of psi onto the equator. Now, any such quantum bit or qubit can be written as a superposition of the 0 vector and the 1 vector. The superposition has a couple of constraints. The coefficients alpha and beta of the superposition have to make the vector have unit length, so that their amplitude squared up to some of 1. And alpha and beta don't have to be real, they can be complex vectors. And in general, they are complex vectors. And we'll see in a moment, due to issues about measurement, when you actually measure a quantum state, it turns out that the state, the qubit psi, and another qubit e to the I zeta psi, whereas zeta is any angle, are in fact the same qubit, in the sense that they give you exactly the same value in every measurement that you make. Now, in practical terms, what this means is a qubit can hold an infinite amount of information. A single qubit can hold all the information in all the libraries in one qubit. But when you go to measure it, if you actually measure a qubit using some operator, you will get a 0 or a 1. So, although you could hold all the information in the world in a single qubit, if you actually try to measure that, you will destroy the information and you'll get a 0 or a 1 out. And in spite of this fact about quantum bits and how they interact with measurement, you can still do interesting stuff. But that's part of the stripping of the gears and thinking in a new way. So the qubits have infinite amount of information, and if you try to look at it, you destroy the infinite amount of information. But you can't, without looking at it, compute with all this infinite amount of information. But you have to be very, very careful how you do it. So because of this relationship, this equivalence, you can, in the general case, write a single qubit psi as the following superposition. Cosine theta, where q theta is the angle between the z-axis and psi. And this is now all a real number, plus e to the I phi, where phi is this angle, times sine theta 1. So that's a general way of representing a quantum bit. Now, to do computing, you need bits and you need gates. You need to operate on your bits. All gates, all operations in quantum computing are unitary. So they are maps from the qubit psi to a new qubit u psi. Unitary gates are linear. So u of a sum alpha I psi I is you just bring the operator in, so it's linear. The conjugate transpose is the inverse. That's what it means to be unitary in terms of matrix representations. And the key thing about the unitary operators, and this is the key, in spite of all the math, the key thing is this, that the unitary operator preserves the length of the state. It takes a unit length qubit and turns it into another unit length qubit. So in a sense, all these unitary operators do, all that the quantum gates can do to a qubit on the Bloch sphere is rotate it around. You rotate the qubits around on that sphere, that's all you can do. So in some sense, very, very simple. The bits are points on the sphere, and all you can do is move those points around on the surface of that sphere. Okay. By the way, feel free to ask questions as we go along.
Can I jump you back a couple of things? Back to the previous, the Bloch sphere. You say that alpha and beta are allowed to be complex numbers.
Yes.
There's a single qubit. I've never seen quantum computing before, so I'm just trying to get my head around it. A single qubit for every point of the two sphere, yes?
Yes, that there's an infinite number of qubits.
So what alphas and betas are allowed? Because if you have any pair of complex numbers, that's a heck of a lot more points.
Yeah, so these are the constraints. The sum of the amplitude squared has to sum to 1. So it keeps it on the surface of the sphere, it keeps it in length. And then you have this other constraint that these are equivalent. So in essence, the constraints do keep you on the surface of that sphere. But the fact that they're complex numbers in general, not real, is what leads to some of the interesting behavior and weirdness and power of quantum computation.
Well, just
Back to that.
the way you've drawn your sort of pure state, 0 and 1, they appear to be reflections of one another.
But in fact, they're not. They're linearly independent.
Why are they drawn on the pole side?
Yeah, so this gets into a very complicated aspect of the mathematics. It actually has to do with a double covering of SU2 onto SO3, and it gets pretty hairy. So we can go into that, but I think it's going to take us, it takes us down a long, long road. I think the best thing to do is to just realize that even though it looks on this diagram like they're linearly dependent, in fact, they're linearly independent. And this is, it gets nasty right away. Okay, so the key thing is the unitary gates are basically just rotations that preserve the length. So let's look at a concrete example, the quantum NOT gate. What it does to the basis states, the 0 and 1 vectors, is it takes 0 to 1 and 1 to 0, obviously. But non-trivially, what it also does is it takes any complex superposition, alpha 0, 0 plus alpha 1, 1, and changes the basis, alpha 0, 1 plus alpha 1, 0. So it also does this operation to any superposition of the basis states. And in terms of matrix formulation, you can actually, the nice thing about quantum computation is it's a simple subset of quantum mechanics. It's actually the simplest subset of quantum mechanics that you can imagine. It's just linear algebra. It's not that hard. So if you take the 0 state and represent it as the vector 1, 0, and the 1 state and represent it as the vector 0, 1, then the NOT the quantum knot operator is simply given by this matrix representation. And we can check it out. So the knot of the state 0, 0 is this vector 1, 0. The knot of that, when you do the multiply through, is 0, 1, which is 1. And it actually works through for all the superpositions. So here, the knot operator is a particular example of a unitary operator that can act on quantum bits and take the knot. Fundamental in quantum computing are the so-called polygates. The first one is the identity operator. The next one is the one we just saw, the knot operator, but it's often called X. So from now on, capital X means the knot operator. And I will mean the identity operator. Y is a very strange operator, where I means root minus 1. And then Z, we'll be using quite a bit later on when we do quantum game theory, is this operator. And it turns out that every 1-bit, 1-qubit unitary gate can be written as a linear combination of these 4. So in that sense, they're universal. You get these 4, you can do any 1-qubit unitary operation. Power. May not always be a very efficient representation, but you can do it. 2-qubit systems, more interesting. You can have 2 qubits, and their composite is written down as a tensor product. Sometimes written this way, and in the physics literature, they'll simplify all the way down. And this is also the same thing as that. It's just the 2 states taken in their tensor product. First is in state psi 1, the second qubit in state psi 2. Now, the 2-qubit systems. So now I'm using the simplest notation, right? So there are 2 qubits here. The first one is in state 0. The second one is in state 0. That's what this work means, okay? It's a 2-qubit system. You can write that in terms of a 4-dimensional vector as the 1, 0, 0, 0 vector. And similarly, you can write the other basis vectors in the tensor product as this. So this one would be the first qubit is in state 0. The second qubit is in state 1. And this is the case where the first and second qubits are both in state 1. And this is the standard mapping that's used in the field between this representation of the basis vectors and an expanded one that you can use. Okay. And now, an interesting, so we've talked about superposition a little bit, the complex superposition. That's one resource. The other resource that we have in quantum computation is entanglement. And here's an example of an entangled state. A state like this was first discovered by Einstein, Podolsky and Rosen in 1935, when Einstein was trying to show that quantum mechanics didn't work, that it was an incomplete representation of reality. So Einstein came up with a state like this, except that that 0 was a 1 and that 1 was 0, but that's another kind of entangled state. And what this means, we'll talk about measurement in a moment, but what Einstein was really interested in was that what this means is if you measure the state of this one, the first qubit, you automatically know what the state of the second qubit is. And similarly, if it's a 0, then the other one's 0. If the first one's a 1, then the other one will be a 1. And Einstein pointed out that if you have 2 electrons, and they're in an entangled state, and they're a billion light years apart, and you just measure the state of one, then you will instantaneously collapse the state of the other faster than the speed of light. And he didn't like that. And so he thought that that was proof that quantum mechanics was an incomplete representation of reality, not the final story. And they finally were able to do an experiment to test Einstein's idea in 1982, and quantum mechanics is right, and Einstein's wrong. This is the way the universe works. So what Einstein thought was a weirdness in the universe that showed that quantum mechanics is false turns out to be, in fact, a computational resource, and I'll show you later on that we can use this computational resource, for example, to resolve the prisoner's dilemma. So this is a non-trivial computational resource, not a weirdness that the spooky action of distance that we should dismiss. And these states are entangled because you cannot in general write this state as a full tensor product of two generic qubits. And in fact, it turns out entanglement is the generic case. If you have two qubits, the generic case, in the sense of probability of it happening, is that they're entangled. This is called the EPR pair for Einstein, but also Rose in 1965. So now you can do operations on 2-qubit systems. If you do, for example, a knot on the first qubit of a pair, that would be, so you have psi 1 and psi 2 are 2 qubits. Then to do a knot in the first pair, would be doing the knot operation there, and you're tacitly doing the identity operation on the second qubit, leaving it alone. So you can write this as a tensor product of the two operators on the tensor product of the two states, standard. And if you do this and just write it out in terms of matrix notation, you're taking the tensor product of the two operators. Remember, this is the quantum knot operator, this is the identity operator, and when you take their tensor product, you get this matrix representation. So if you act with this on the 4-element vector representations of the basis states, you will get the right thing. So this is an operator on 2 qubits, but it's a tensor product. It's not a genuine non-trivial operator on 2 qubits. There are some, though, and the one of interest we'll look at is the controlled knot. This is a genuine 2-qubit operator. It takes 2 qubits and does something non-trivial on it. The controlled knot, if the first qubit is 0, you leave the second qubit alone. If the first qubit is 1, you switch the second qubit. So the first qubit is the control. If it's a 0, do nothing. If it's a 1, flip the second qubit. That's the idea of the controlled knot. Okay? So here, the first one's 0, so you leave the second one alone. Here, again, the first one is 0, you leave it alone. But if the first qubit is 1, then you flip the 0 to a 1. If the first qubit is 1, you flip that 1 to a 0. That's what a control knot does. And that's the matrix representation of that you can compute. Pretty straightforward. By the way, I don't expect you to see that that's the matrix representation, but I'm going through quickly because it's long. Now measurement. Suppose you have a set of qubits, phi, that are an orthonormal basis for the system of interest, and you have some arbitrary state psi, which is a superposition of those states phi. Then if you measure, and you do a von Neumann measurement to find out what is the actual state of psi, which of the phi is it, the probability that you'll get the answer phi sub I is the amplitude squared of the complex coefficient phi. This is where the weirdness of quantum mechanics comes in great detail. So the state, initially, the state psi is a superposition of all these bases. When you make the measurement, you will get one of the phi coming out as the answer, maybe the state 0, maybe the state 1. And then the new state has collapsed. If it was a superposition of 0 and 1, now it's just either 0 or 1. It's not a superposition. So measurement actually changes what's being observed, where the amplitude squared is the standard thing. And the reason why e to the I psi is the same thing as psi is because if you look at what we just looked at before, e to the I psi is the same thing as alpha e to the I psi phi, because psi is just the sum of alpha I phi.
We're using I in 2 very different ways.
Unfortunately, yes, that's right. I is now not being used as root minus 1 in here. And there it is, unfortunately. Yes. This is this is standard in the quantum computing literature. It's actually standard. It would be actually, I think, better for me to have used J. Unless you're an engineer, then J means root minus 1. So, K. So, then in this case, the probability of getting the outcome phi sub I when you measure would be this amplitude squared. But these two components just cancel, and you just get back to the original. So the result is that because it makes no difference in measurement, EI, theta, psi, and psi are the same state because they have the same results in measurement. Yeah.
Can you just remind me what it means to take a scalar times a qubit?
Well, think of the qubits as vectors, and it's a complex. It's not just a scalar; it's a complex number. You're doing a complex superposition of all these different qubits, and it better still end up on the surface of the sphere. So you can't just do any scalars you want. You have to.
Oh, so but the alphas, if we're taking the sum is.
These alphas all have to. Their amplitude squared have to sum up to 1.
They all have to.
Yeah. So the sum of the alpha I amplitude squared equals 1. So that you keep this thing a unit vector. That's the key.
Yeah, and this is a finite number.
For quantum computation, there it is. In quantum mechanics, more generally, of course, you get nasty. The nice thing about quantum computation is it's all finite. Quantum circuit. You might start off with 4 qubits, all say in the state 0. Typical thing to start them off in the state 0. And then you might have a single qubit gate, a unitary operator U1, and then maybe a 3 qubit gate U2 that will entangle 3 qubits, do some operation on them. Another one that does entangles these 2 and so forth. And then we'll talk about these. These are measurement operators at the end. The measurement gates are the only non-unitary gates in the whole thing. Everything is unitary. It's all reversible. All quantum computations are reversible except measurement. That's irreversible. So you would start off the state psi initially would be this tensor product of 0, 0, 0. At the end, you'd have some state psi f. Here's the measurement gate. Its representation. So you start off with some qubit, which is in the state alpha 0 times 0 plus alpha 1 times 1. Then this gate, what it does is it gives you the state B, where B is either 0 or 1. B is 0 or 1. You get the state B, and you print out, in some sense, B, 0 or 1. Where the probability that you get B is the coefficient, alpha 0 or alpha 1 squared. Alpha is B squared. So the measurement gate will take this state, and it'll either give you 0 or 1 as the output here, with probability alpha 0 squared or alpha 1 squared for those outputs. That's what the measurement gate does. It collapses, it fundamentally changes the state. A very powerful gate, used all the time, is the Hadamard gate. The Hadamard gate takes the state 0 and maps it into the, again, the unit vector state of 1 over root 2, 0 plus 1. And it takes the state 1 and maps it into 0 minus 1. So notice it's taking one of the basis states and mapping it into a superposition state. And that's going to be the key. Quantum computation, you'll start off with a classical state, so to speak. You'll put it into a superposition state, and then you can, in some sense, start computing in parallel over all the superpositions and get all this power. So one of the things you do in quantum computation, start off with the states, run a Hadamard gate over all of them so they're in superpositions, and then you can just use the superposition as your quantum resource. Tremendous things. So it's a very powerful gate. Simple representation. And in fact, this is the quantum computation analog of the discrete Fourier transform. And it's all inverse. The Bell basis. You can, if you have 2 qubits, and they're in states like 0, 0, 0, 1, 1, 0, and 1, 1, you can translate them or transform them into the Bell basis. And this I'll just, without going in too long, essentially these are, you start off with 0, 0, 1, 1. These are unentangled states. The computational basis states are unentangled, they're separable. And in the Bell basis, you have these entangled states. And this is again going to be another computational resource that we'll see is very, very powerful in computing. And this is a circuit that can change from the normal basis states like 0s and 1s. You do a Hadamard, a controlled knot. This little thing is the controlled knot operator. That's the control, that's the knot. And it will take you into the Bell basis. So if you start off, for example, with the state 0, 0, I is 0, j is 0. Then after you do the Hadamard, get to state phi 2. Phi 2 will be, the Hadamard of 0 is 1 over root 2, 0 plus 1, as we saw. And then you still have the second state, that 0 is that 0. So all we've done is taken the first qubit that was 0, make it into this superposition. The second qubit got left alone. Okay? So that's the state of P 2. Then, and that's the same thing, now this is just distributing the 0 over that. Okay? So you just distribute it. Then, at this state, after you do the controlled knot, you get the new state. Since this one was 0, you don't change that one, but because this one was 1, you do the controlled knot, and that 0 gets turned to 1. Okay? So this is, and what this does is it changes the 0, 0 into this state, which is the Bell state, B beta 0, 0. That was okay. That's beta 0, 0. If you have two qubits that are in the classical basis states, this is a little circuit that will actually change it into the Bell basis, and then you can do a measurement in the Bell basis, the ones we just looked at. This is, again, a trick that's done all the time. Okay, we're going to use this now for some interesting stuff, but first, one of the most counterintuitive facts about quantum computing. In classical computing, we don't think about copying bits. It's obvious that you can take a bit and copy it. You cannot do that in quantum computing. There's a no cloning theorem. You cannot copy the quantum bit. If you copy it, you destroy the original. That's the only way to copy it. You have to destroy the original. It's quite strange. How can you possibly do computation if you can't clone stuff? Well, you have to be clever about it. So there is no unitary operator U that will take some state of interest psi and then some empty state, 0, and then copy psi onto that second qubit. There's nothing, there's no unitary operator that will do that. And the proof very simply is that it follows just from linearity. So if you take U of a superposition of A psi plus B phi, where A and B are complex, and you try to copy that onto 0, well, that by linearity, that means it's A of U psi 0 plus B of U phi 0, just linearity. And then if you could actually copy, you would get this, A psi psi plus B phi phi, that's what you get. But if the unitary operator were truly a generic copier, then you should be able to take U of A psi plus B phi and actually copy that whole thing into 0. You should be able to do this. So there's the A psi plus B phi, and there's the A psi plus B phi again. If there was a truly a generic copier, you should be able to do that. But if you expand that out, what that is this, and that do not agree. So, end of story. You cannot copy a quantum bit. No cloning. However, you can teleport them, sort of like Kirk in Enterprise. You can teleport them, and you can teleport them using only 2 classical bits of information. You can send a qubit with an infinite amount of information as far as you want. It's truly remarkable. So we're actually going to do quantum teleportation. So you have 2 people, Alice and Bob. And Alice and Bob always show up in the quantum computation literature. Alice has a qubit psi that she wants to send to Bob. To make this happen, Bob and Alice each have an electron. And the electrons have been entangled. In fact, they're entangled in the state beta 0, 0. This state we've looked at a few times now. So Alice and Bob each have an electron. It's in this, they're entangled in state beta 0, 0. And now Alice and Bob move light years apart from each other. They're a long, long way away. They share this EPR pair. Okay? Turns out, if you go through the algebra, and it's just linear algebra, the state psi, which is Alice's, and beta 0, 0, which is the 2 qubits, right? It's a 2-qubit state, and they're sharing the qubit. This state psi beta 0, 0 is equal to this following thing, beta 0, 0 psi. Now, the order is important. right? The order of the qubits is absolutely important. We are not reversing the order. What this means is that even though this is psi beta 00 here, if you do some algebra, it turns out that you can think of that qubit and that qubit as entangled. And the entangled state is beta 00 with probability 1/2. And then the other state here is psi. Or, and this is a classical superposition. It's 1/2 beta 01, that's the next Bell basis, times the not operator of psi, and so forth. So these are all 4 Bell bases. And what's happening is now we've switched from having psi there and beta 00 here to this is now the Bell basis, and this has some version of psi acted on. So as a result, all Alice has to do to teleport her bit psi to Bob is she just has to do a Bell measurement on her state psi, her qubit psi, and her electron, part of her EPR pair. So she does a Bell measurement on her electron and her state psi, and she's going to get out a 0 or a 1 here, a 0 or a 1 state there. Okay? If it's, and then all she has to do then is send those 2 classical bits. These are now classical channels. She sends whether A is 0 or 1 to Bob, classically. So that's at the speed of light, not faster than the speed of light. Right? And she sends B, which is 0, 1 to Bob, again at the speed of light, not faster. And based on that, Bob does the following. If A and B are both 0, then he does nothing, and he gets the state psi. His qubit is already in the state psi. If he gets a 0 and a 1 from Alice, then he knows that his qubit is in the state x psi. So all he has to do is x, because x is the inverse of x. So it undoes x. So he knows that if he gets a 0 and 1 from Alice, all he has to do is an x to his state, and he's got psi. If he gets a 1, 0 from Alice, then he knows his state is z psi, so he just does a z, because z undoes itself. And then finally, same down here. If it's 1, 1, then it's xz, he just has to do a zx, he's got an active psi. So you can send an infinite amount of information as far as you want at the speed of light by sending only 2 classical bits. That's quantum teleportation. So you can't clone, but you can do something that's, in some sense, much niftier. Classical algorithms, you have classical probabilities going from state 0 to various other states. I'm going to zip through this. This is probability of final outcome is 2, would be the probability that you go from there to 2 and all the possibilities, sum them all up. Probabilistic algorithm with the quantum setting, you would have amplitudes, but you, in some sense, collapse all these amplitudes by measuring and just get, again, classical probabilities in each case. So in that case, probability going from 0 to j is the amplitude from 0 to j squared, and so forth. And the probability, the final outcome is 2, would be this classical probability, which can be rewritten that way. But in quantum, it's very, very different. You don't collapse the amplitude, you don't look, you don't measure, you just deal with amplitudes, not probabilities. The probability of the final outcome is 2, is the sum of the amplitudes of going from 0 to all these possibilities, and from those possibilities to 2. And that's not the same as the classical. What this allows you to do is have interference of the pathways. The various paths can interfere. That's where you get the quantum power. Quantum computation, you have, in many cases, infinite horsepower in your computation, as long as you don't look. If you look at the computation, you destroy the interference. But if you don't look, you have infinite horsepower. And this leads to a different notion of intelligence, going back to cognitive science. We have a notion of intelligence, which is intelligent behavior is a computational procedure that you can see step by step what the computation is doing in pursuit of a goal of interest. That's what intelligence is to our field right now. And you can trace the algorithm. You can see step by step what it's doing. What quantum mechanics seems to be telling us is that what we thought was intelligence is in fact stupidity. It's the straitjacket of intelligence. Because if you insist on seeing step by step what the algorithm is doing, you destroy all the power of superposition and entanglement. You lose the essentially infinite horsepower that you have. So intelligence is what happens when you can't see and when we don't see what's going on. This leads already to a very different way of thinking about intelligence than I've ever thought of before. Game theory. I figured that for many in this audience, the application of game theory would be the most interesting way to convince you that this might be something to pursue. So here's a couple games. The spin flip game. Alice and Bob show up again. There's an electron which we're going to play with. It can have either state U, which is up, say the 0 state, or D, which is down, the 1 state. Okay. And in this game, Alice always first puts the electron in the up state. That's our standard opening move in this game. So Alice sets the electron in the up state, the 0 state. Now Bob gets his choice in this game. He can either do the identity operator, so he leaves it in the up state, or he can do the not operator and he flips it to the down state. So Bob gets his choice. Alice is ignorant about what Bob's doing in this game. So if he does the identity, he stays U. If he does the not, it goes to down. Okay? Then it's Alice's turn. She doesn't know what Bob did. She gets her chance to do the identity or the not operator. And then Bob gets the last move in this game. He doesn't know what Alice did, but he gets to do the identity or the not operator. Okay? And then you measure the state of the electron, and it's, you set the payoffs that if it's up, Bob wins a buck, and if it's down, Alice wins a buck. That's the key. So here's the spin flip sequences that could happen. On the top in blue are Bob's moves. Bob moves first, and then the red is Alice's moves. So for example, in this box right here, Bob moves first, does an X, then Alice does her I, and then Bob does his X. That's how I'm sure of this. So this table gives you all the possible sequences of moves in this spin flip game. Okay? As a result, if we look at what happens, so the state is originally in the up state, the electron's in the up state. If Bob does the not, then it's in the down state. Then if Alice does nothing, it stays down. Then Bob does a not, it goes to the up state again. Okay, so that's how. So these sequences are just showing you how the state of the electron is changing as the game proceeds, and each player makes their move. Okay. And these are the payoffs to Alice. If we just go back, the final state here is U. The final state here is D. If it's U, she loses a buck. If it's D, she gets a buck. And that's everywhere that's +1, it would end up being D. Everywhere -1. So these are the payoff. This is the payoff matrix based on the state of the qubit at the end of the game. Now, Bob goes 1. All right, so all the moves right now are in some sense classical, knots, identity operated. Bob's got a trick up his sleeve. So we'll assume that Alice has a mixed strategy. She equally plays doing nothing or taking the knot. That's her mixed strategy. Bob goes Hadamard on this thing. So remember the Hadamard operator is this operator, and here's how he does it. So Bob plays H. H of U. So that's the up state, and that's the H operator. Is that which is, as we saw before, it's just what Bob is doing is he's putting the game into a superposition of up and down states. It's not just up or down, it's a superposition. That's where he's going to get his power here. Alice plays her mixed strategy, which leaves U plus D unchanged. Okay. Then Bob plays Hadamard again. Now when Bob plays Hadamard again, let's look at what happens to him. He does H of HU, which is 1 over root, here's the H again. Now we're taking this version of the HU, now this one, to compute with. So there's HU. So this is, the HU there is this thing, and that's the H there. You do the simple matrix multiply, you get that, and that's U. Bob will win every time. There's nothing Alice can do. If Alice plays classical, Bob goes quantum, Bob will always win. That's the power of quantum. Prisoner's Dilemma, another interesting game. Alice and Bob. Standard Prisoner's Dilemma payoff, right? In this case, this is the Nash equilibrium. C means cooperate, D means defect. And the standard thing is that the Nash equilibrium is here. Alice knows that she should defect. If Bob defects, her best payoff is if she defects. And if Bob cooperates, her best payoff is if she defects. So no matter what Bob does, she should defect. And Bob has the same analysis. As a result, that's the Nash equilibrium. However, it's not Pareto optimal because clearly they'd be better off if they both cooperated. They both end up with something nice. That's the source of the prisoner's dilemma. If you do what you should do to maximize your payoff, you end up messing yourself up. That's the prisoner's dilemma. But technically, the Nash equilibrium is not Pareto optimal. Okay, now we can do quantum on this. A and B each have a qubit. The state 0 means I'm cooperating, 1 means I'm defecting. Initially, you apply some unitary operator to the pair of qubits. This is Alice's, that's Bob's qubit. Alice will have some strategy, a unitary operator, use of A. Bob will have some strategy, unitary operator, use of B. They're going to act. The result is a tensor operator on the, so U is the initial thing we did here. This is now Bob and Alice doing their thing. Then we invert, we undo this U, so the adjoint is the inverse. So this is the way to invert that. This gives us our final state of the qubits, and then we measure and pay off. So that's how you're going to do this quantum prisoner's dilemma game. And here's the deal. So the payoff, Alice the standard payoff. And you can compute it in terms of the actual quantum amplitudes. We won't go to it because of time. Suppose that this U is this operator right here. So that the acting with U on the 2 qubit puts them in this state. Okay. So suppose that we can arrange that. So it just puts it in a superposition and entangled state, the 2 qubits. Now, if they both cooperate, they both do the identity operator, this is what will happen in the final output. If Alice defects, you get this state. This is Alice defecting, Bob cooperating. If Bob defects, so Alice is cooperating, she doesn't do anything, but Bob defects. And if they both defect, and they both do the not operator, and this would be the final quantum state of their 2 qubit pairs. Okay? And it turns out that when you measure, you will get 0, 0. If they both cooperate, you'll get 0, 0 with probability 1. If Alice defects, you'll get the state 1, 0 with probability 1, and so forth. And so the quantum game contains the classical as a special case. But now it's interesting. Suppose Bob was Hadamard. We didn't go through all the computations, but it turns out here's the new payoff matrix. We get a new Nash equilibrium. This strategy is no longer the Nash equilibrium. The quantum strategy trumps the X strategy, the not strategy, the non-cooperative strategy. It's not Pareto optimal, but we can fix that. If we go to the quantum Z operator, if Bob does that, then we get a new Nash equilibrium, which is Pareto optimal. End of prisoner's dilemma. There's no prisoner's dilemma. So the prisoner's dilemma may be an artifact of our classical mode of thinking, not something fundamental.
Question.
Yes.
I know what entanglement between Alice and Bob means in the classical sense, but I'm trying to understand what physical intuition there is in entanglement between Alice and Bob in the quantum sense.
Well, the entanglement is between their electrons. And it's a weird property, but essentially what entanglement about two electrons is telling us is that we, in our classical way of thinking, think of the two electrons as separate entities. And what quantum mechanics is telling us is that it's an artifact of our way of representation. In fact, there's an underlying unity that's escaping our way of representing.
You're talking about Alice and Bob, you're talking about people, not electrons.
But when I should be careful. It wasn't Alice and Bob that are entangled, it's their electron. Their electron pairs.
Well, which electron? You got a lot of electrons.
So the way it's set up is, when you play the game, is you have two electrons, you put them in an entangled state, right? If you, Hadamard operator, for example, put them in an electron in an entangled state, then Alice and Bob each take one of the electrons and go away and start playing with their electron.
Just don't understand what that physics is.
Well, we'll have to go into that.
Show me how to put my electron into Hadamard's.
Okay. Well, you can do that actually with, for example, with polarized light. There are these down converters, these crystals. You can put a photon of light through, has energy E. Out come two photons with half the energy, and they're in a polarization entangled state. There are actually physical devices to do this. In terms of evolutionary game theory, if you have, again, an evolutionary game situation in which you have the prisoner's dilemma payoff situation. So it's the classical, this is the classical situation. You will get, this is the Nash equilibrium. It's also an evolutionary stable strategy. So it will, if a mutant comes in, an I mutant comes in, it'll be destroyed. That's what it means to be evolutionary stable. So it's Nash and evolutionary stable. However, if these classical players are going along and all of a sudden a quantum mutant comes into the game, the quantum mutant will drive the classical players to extinction. This now the H strategy, the mutant strategy, is Nash and evolutionary stable. And that quantum guy can be wiped out by, so the H invades the X. So the X guy was fat and happy, he was ruling the world. The quantum mutant comes in and he destroys him, drives him extinct. But then along comes the mutant Z strategy, and it's also Nash and evolutionary stable, and this guy will drive the mutant H and X to extinction. So evolutionarily speaking, if you do quantum moves, you can have the upper hand over all classical players in many cases and drive them to extinction. So, obvious questions. Micro versus macro, this is one. Don't superposition and entanglement only apply to microscopic particles? And isn't the brain macroscopic and isn't cognition macroscopic? Well, so maybe all this is irrelevant to human cognition. I think that's a little too fast. I'm going to give a couple examples to stimulate some discussion. I'm sure there'll be questions on this point and we'll go into them. But I want to suggest that maybe there is superposition and entanglement where we might not have expected them. Consider the Necker cube. Sometimes you can see that interpretation of the Necker cube. I'll call that interpretation 0. And sometimes you can see that interpretation of the Necker cube. Let's call that interpretation 1. The question is, what interpretation should we write down? What is the right interpretation of the cube when you don't look? Is it 0 or 1? Well, so what is the state of the cube when you don't look? How about this? Why not a superposition of the 0 and 1 states? So the argument that says, we see superpositions in the microscopic realm, but we never see superpositions in the macroscopic realm. In fact, it's hard to know what it would even mean to see a superposition in the macroscopic realm, is making a fundamental mistake. We actually never see superpositions in the microscopic realm. Whenever you see in the micro realm, you've made a measurement and you collapse. So you never see a superposition in the micro realm. You write down superpositions for the state when you're not looking. You're forced by the empirical evidence to write down the superposition in the micro realm when you're not looking. But that seems to be what we're being forced to do in the macro realm as well. when you're not looking, what's the right state to write down for the necrocube? Seems to be superposition. One other one. How about entanglement? That's superposition. What about entanglement? Surely that could be in the macro realm as well. Well, let's look at this edge as a separate object, and that green edge is a separate object. And I'm going to say that I'll call it state 0 if it's near to me, and I'll call it state 1 if it seems far. And as you look at this cube, sometimes you see the red line is near, and sometimes you see it as far. Okay? As it flips. So, what is the state of the cube when you're not looking? Well, the right thing to write down is that if the red guy is near, the green guy is far, or if the red guy is far, the green guy is near. The right thing to write down is that the state when you're not looking is a superposition of the two, and this is precisely the entangled state. In fact, this is the EPR state that Einstein could also be closing. So, our entanglement, so what does this mean? I think that it follows from what, another thing I'll just mention briefly, and that is a view about perception in general. That perception, the goal of perception is not to tell you the truth about the reality. Perception is a simple user interface. And I'll just give you an example. Here's a Mac interface. Here's an icon for a file that you're writing. That icon is blue, roughly rectangular, in the lower right-hand corner of the screen. But that doesn't mean that the file itself is blue, rectangular, or in the lower right-hand corner of the computer. That's not what it means at all. The whole point, the whole reason user interface is useful is it does not resemble what it represents. It simplifies. So perhaps what quantum theory, what the superposition and entanglement is telling us, and the necrocube example is telling us, is that we're getting these superpositions and entanglements because our way of representing the world is not the truth. It's just our simple user interface. The truth itself, if we're going to force ourselves to write a description of reality in the language of our interface, then we're forced to write superpositions because reality actually doesn't fit into our categories. So as soon as we try to describe reality, when we're not looking in terms of our categories, we're forced to use superpositions. That's what this seems to be telling us.
Is your lecture almost finished? I don't mean to interrupt.
This, I think, is basically the last slide. I was just going to say that there are others who are actually doing quantum in cognitive science, and that was it.
After we're going to clap. I know very little about quantum computation, areas of probability and so on. But the natural question I would ask is, it would seem to me, and of course, there's two areas it seems to source from. One is conformal mapping, unitary conformal maps, of course, and the other, closer to home, is set probability or random set analysis. It seems to be an intimate relationship between looking at things in terms of sets instead of single points. And certainly your examples for the cognitive science examples can be put in a random set viewpoint, or at least a set analysis if you don't want to find probability to sets of reality. So what's your comment on that?
Well, there's been a lot of fundamental work in terms of rethinking what the quantum formalism means in terms of other formulas. There's a quantum logical approach. There's a bunch of approaches. What you're saying is actually being heavily pursued by a lot of people. There's lots of directions to go like that to try to make sense in other formats of the quantum formula. And perhaps cognitive science could be helped by thinking in terms of those formulas. Yes?
So I have a question regarding your caveat at the beginning about the burden of proof. What reasons are there for thinking that neurons implement circuits that compute, that do quantum computations as opposed to classical computations? So is there more evidence that neurons implement classical circuitry or quantum circuitry?
Well, the issue about circuitry per se, there are papers that have been published where people give arguments on grounds of decoherence and so forth, that you're not going to have coherence long enough at the level of the size and temperature of neurons to have quantum computations going on. But, you know, there are some papers that are starting to explore and get empirical evidence for the possibility of quantum computation in modeling decision theory and the temporal dynamics. When you have something like an cube that's multi-stable, and you look at the flipping times, you can use quantum evolution to get empirically different predictions than the classical evolutionary models. And you can start to then turn this into not just a hand wave, but an actual empirical issue. And it turns out it's not either or. There's the classical, there's the quantum, and then you can use so-called density matrices to actually look at any in-between state, from the purely classical to the purely quantum, by essentially having a parameter for how much decoherence is there. So the real question for us to pursue in cognitive science is not just the either or, but how much decoherence is there in the system? Is it purely classical, completely noisy, or is it pure superposition? Where in that? And as you move that parameter back and forth, you will get different empirical predictions. We should go measure them. If it turns out that we're finding evidence for superposition, for quantum computation, at least to some extent, and we can't get that from neurons, maybe we need to look at a sub-neuronal level for where the action, we actually don't know where the action is in the brain for computation. We think it might be spiking right, but there's a lot of stuff we can't explain. So this empirical approach may then feed back and completely revolutionize what we think, what aspects of the brain should be viewed as the computational aspects. Maybe it's not the spiking rate.
Go back to the prisoner's dilemma.
Yes.
You may remember the original story. Alice and Bob were picked up because they were thought to have committed a crime.
That's right.
And then separated and
That's
had to
right.
make a decision whether to confess or not confess. And do I envisage that they are carrying an entangled neuron when they commit the crime, and then in the police station they then proceed to operate?
Well, yeah, they each will have, not an entangled neuron, but an entangled particle.
Particle, sorry,
Yeah.
I didn't mean neuron.
Yeah, a photon or electron would do. Any particle that you can have entangled. So Alice and Bob get caught, but before they got caught, they had taken 2 electrons, done a Hadamard on them. I got mine, you got yours. You go to your cells.
You're essentially saying that any criminals,
They get a hold of
they
this.
should have.
They can beat the system. That's right. So as long as they can, you know, an electron's pretty small. So you can stick it into the cell pretty well.
A little small, a little hard to handle.
Yeah, you need some real clever apparatuses to do these little tricks on the electron when no one's looking.
Police might notice.
That's right. Excuse me, officer, while I go into a superposition over here. Yes.
It's my impression, if we're going to go into the story of the prisoner's dilemma, that the jailers are going to ask guilty or innocent, and beforehand they can choose some strategy for choosing guilty or innocent, but the jailer's not going to ask what spin state are you giving as your plea. So I'm not sure, like how much is this expanding the game and making it more interesting and illustrating the point? How much is it actually changing the game to a completely different game that allows for answers?
Well, in some sense, by showing that it contains the classical game as a special case, that's the first point that needs to be remembered. It contains the classical game as a special case. It does extend the game in a fundamentally new way. In fact, it allows you to completely resolve the prisoner's dilemma. So in some sense, it is a new game if you allow quantum moves, and you will beat out the classical players.
But how is that different from a classical game that now has 4 monsters that still contains the classical prisoner's dilemma as a subgame?
Yeah, so in that sense, it's very, very similar. It's just that the moves here are pretty powerful. I mean, like, for example, Bob can always win.
Just a question about the moves again. A couple of us have the same confusion.
Yes.
Are the moves that you say, you maybe not think about these moves from the classical viewpoint, but are these moves within the full classical setting, even though you didn't know to do those moves? Could they be put in the full classical setting of the game?
Well, they're actually moves that...
Because you set it up as utilities and so on.
They take you into states that the classical game doesn't recognize, right? Instead of cooperate or defect. These new moves, like the Hadamard operator, take you into a state that's not cooperate, not defect, it's both and neither.
But
It's a
it's
superposition.
still, in classical analysis, you don't have to just cooperate or defect. You can do other things.
You can do a mixed
There's an
strategy.
infinity of things you can do.
Well, there's a lot of, so there are classical mixed strategies that you can do, but this is even more powerful than a classical mixed strategy. This is a true complex superposition in general. So that
So it
gives
cannot
you,
be formulated in any classical
it
setting.
actually transcends the classical, absolutely. Yes.
I guess the only paper I recognize is the one by Usman.
Yes.
And it seemed to me, in his application is somewhat similar to your dichotomous state in the Macroscopic zone. And the problem that I have with that is that the state that you are in would correspond to a measurement. Who decides when the measurement gets taken? And once the measurement is taken, unless the state evolves, it stays there. It has no memory. You cannot ask such an observer, do you recall ever being in another state than the one I just measured you being in? They have no memory.
Great question. The paper by Hoffman, I think Biological Cybernetics 2004, it sort of gets at this. It's very interesting. He's looking at the flipping times in the perception of the necrocube and getting a quantum model of that. He uses the so-called quantum Zeno effect. So if you have, so he imagines that the two states, that there's a Hamiltonian, H, and the unitary operator is e to the IHD. And so, and the states are going to evolve from one to the other, and that will give you sort of your natural flipping time from one state to the other if you don't look. But then he assumes that there's some rate at which you have this internal observation process. It has its own temporal parameter. And in quantum mechanics, it's very,
You have a clock.
an internal clock, but it's a random clock. And in quantum mechanics, it's really remarkable. If you measure, you collapse. So suppose you have, this is the upstate, that's the downstate, and you have a process that's going to slowly rotate from the upstate to the downstate. And if you don't look, it'll do that in, say, 2 seconds. But as it starts to rotate, if you look at it, say, just a quarter second into it, you'll probably get the upstate. And so it'll be back in the upstate. And then it starts to rotate, and you look again, and it's back in the upstate. If you keep looking at it, it will never evolve. A watched pot never boils. And this is called the quantum Zeno effect. If you actually look at something that's evolving, you can stop it from evolving, because the active observation actually changes the state. So Oppmann-Spotker actually assumes that there's this natural rotation from the one version of the cube to the other, and then there's this internal rate at which you look at the state of the cube, and that will sometimes flip you back, sometimes not. And he puts them all together to actually get an empirical model of the switching times. Quite nice. So the kind of stuff you're talking about is being looked at by the people in the field. It leads not to problems, but to very, very interesting models.
Yeah, but why would that rather interesting but elaborate theoretical description, what empirical evidence would suggest that that is more satisfactory than a straightforward, probably much simpler, classical description?
Well, in the case of the paper by Fuss and Navarro, what they show is that you can get some binary, now it's for decisions, and you're looking at like Bernoulli random walks to the boundary versus quantum walks, Hadamard walks to the boundary. And it turns out that the first arrival times have different forms of distributions in the two cases. It's empirically different. So if you have it's bimodal in the quantum, unimodal in the classical. So you can actually get empirical evidence that would tell them apart.
But then Navarro would also give you a model in which you have two counters that can have different properties. You don't, okay, I understand that the quantum walk can be approaching both boundaries in some sense at the same time. So why not two classical counters? One of which is counting increments toward one boundary and one of which is doing the job for the other.
Well, might want to talk afterwards, but one thing I will say that's of interest, and that is that with the quantum, you can explore all possibilities of terror. And so this leads to another very interesting aspect for cognitive science.
Provided you don't walk.
That's right. Provided you don't look.
Very inconvenient.
But necessary. Thank you very much.